So the number of ways of ordering n objects is n factorial. The number of ways of choosing k objects out of n is n choose k, which is n factorial over k factorial, n minus k factorial. And this is where I don't care about the order at which I choose these k objects out of the n. So the order doesn't matter. Right, so a way to think about that is imagine that they are identical. Now let's imagine the alternative situation where the objects that I'm choosing are not identical, they're distinct. If I want to choose k of them out of n, then I have n, the permutations of n and k, which is going to be n factorial over n minus k factorial. So the difference between these two things is a division by k factorial, which essentially will remove the overcounting, which occurs if the objects are identical. Right, so this assumes that the objects are distinct or distinguishable. So we have applications from 6 universities for hosting a tennis championship in 2 different years, 2008 and 2009. How many ways may they be selected? So first of all, we are not allowed to be held at the same university. So in the first year, in 2008, I have 6 choices. And in the second year, 2009, I now only have 5 choices because I'm not allowed to choose whichever one I chose in the first year. So the answer is 6 times 5, which is 30. Alternatively, we can think of this as being taking n, the n objects, and choosing 2 of them where the order matters. So therefore we have 6 factorial over 6 minus 2 factorial, which will be 6 times 5 times 4 times 3 times 2 times 1, divided by 4 times 3 times 2 times 1. So this cancels with this, and we're just left with 6 times 5, which again is 30. And then in part B, they're allowed to be held at the same university. So in the first year I have 6 choices, and the second year I have 6 choices. So the answer is 36. So we've got 5 finalists, so n is 5. How many ways can we choose a winner and a first runner-up? So we've got 2 positions that we want to fill, the winner and second place. Now, there's 5 people who can be chosen as the winner, but whoever is chosen as the winner can't also be second place. So there's only 4 choices for second place. So the answer is 20, 5 times 4. Alternatively, it's just 5 P2. So 5 factorial over 3 factorial, which is 20. So now we have 4 candidates for mayor, 5 candidates for city treasurer, 2 candidates for county attorney. In how many ways may voters mark their ballots if they vote in all 3 races? Okay. So we have 4 possibilities for mayor, we have 5 possibilities for city treasurer, and we have 2 for the county attorney. So we've got 20 times 2 is 40 ways of voting. And then secondly, if we exercise our right not to vote in any or all of the races, so this just adds an extra vote to each position. So there's the 4 candidates for mayor, plus the ability to not vote for anyone. So we just increase each one of these by 1. So now we have 5 times 6 times 3, which is going to be 5 6s are 30 times 3 is 90. A multiple choice test has 15 questions. Each has 5 alternatives. In how many ways may a student fill in the answers if they answer each question? So question 1 has 5 possibilities, question 2 has 5 possibilities, and so on, all the way down to question 15. They all have 5 possibilities. So we multiply 5 by itself 15 times, or the answer is 5 to the power of 15. A television director is scheduling a certain sponsor's commercials for an upcoming broadcast. There are 6 slots available. In how many ways may the director schedule the commercials? First of all, if the sponsor has 6 different commercials, each to be shown only once. So I have 6 slots. If I have 6 commercials to be shown once, then in the first slot I have 5 options. In the first slot I have 6 options. In the second I have 5. The third I have 4 options, and so on and so on. So the answer is just 6 factorial. For part B, we still have 6 slots, but now we only have 3 commercials, and each is going to be shown twice. So what we do now is we take the 6 factorial ways of combining these 6 commercials, but then for each pair of commercials which are duplicates of each other, we divide by 2 factorial for each one. So our answer here will be, well, up here is 720 for 6 factorial. This is 720 over 2 times 2 times 2, which will be 90. And then for C, we have a similar idea, except now we only have 2 commercials and each is shown 3 times. So we divide by 3 factorial twice. And we get 20. Finally for D, the sponsor has 3 different commercials. The first will be shown 3 times, the second 2 times, and the third once. So 6 factorial ways of rearranging these things all together. We divide by 3 factorial for the one that's shown 3 times, 2 factorial for the one that's shown twice, and 1 factorial for the one that's shown only once. Right, 1 factorial is just 1, so we just ignore it. And then we get 60. How many ways can 5 people line up to get on a bus? Well, in the first position there's 5 options, then in the second position there's 4, in the third position there's 3, and so on and so on. The answer is 5 factorial. So this one's a little bit trickier. How many ways may these same people line up if 2 of them refuse to stand next to each other? So the easiest way to think about this is, so the number of ways these 2 people are not together is going to be the total number of ways that these 5 people can stand together, which was 5 factorial, minus the number of ways that they are stood together. And it's much easier to calculate the number of ways that they are stood together, because what we can do is, if we picture our 5 people like so, we can now just pretend that these 2 people who need to be stood together all the time act as one person. So now we just have 4 people stood in a line. And the answer is, how many times can these 4 people be rearranged? And the answer is 4 factorial. But then we need to multiply by 2, because for each arrangement of the 4 people here, remember that one of these people actually represents 2. So for each arrangement of the 4 people, the person that represents 2, they can swap around. So the answer is actually 4 factorial, 2 factorial. So our answer will be 5 factorial minus 4 factorial, 2 factorial, which comes out as 72. How many ways can 8 people form a circle for a folk dance? So 8 people can be arranged in 8 factorial ways, but because this is a circle, we have to divide by 8 to account for the symmetry of the problem. So the answer is actually 7 factorial. Question 9, how many permutations are in the letters of the word great? Well, we have 5 distinct letters, so the answer is just 5 factorial. Question 10, we now have the word greet, so we have 5 letters, but 2 of them are repeated, so we have 5 factorial divided by 2 factorial. 11, a similar idea. We need to count the total number of letters, and we need to know how many letters are repeated and how many times they're repeated. So the word statistics has 10 letters, so we can rearrange these letters in 10 factorial different ways. But to account for the 3 S's, I divide by 3 factorial. To account for the 3 T's, I divide by 3 factorial. And to account for the 2 I's, I divide by 2 factorial. So a college football team plays 10 games during the season. In how many ways can it end the season with 5 wins, 4 losses and 1 ties? So we have 10 factorial possible ways of rearranging these games. If I want 5 wins, I divide by 5 factorial. 4 losses, I divide by 4 factorial. 1 tie, I divide by 1 factorial. Similar idea for question 14. 8 people, so 8 factorial on the top. 3 order the chicken, 3 factorial. 4 order steak, 4 factorial. 1 orders lobster, divide by 1 factorial. So we have a true-false test with 20 questions. In how many ways may a student mark the test if each question is answered? So 2 choices per question, 20 questions. So the answer is 2 to the 20. In how many ways may a student mark the test if 7 questions are marked correctly and 13 incorrectly? So notice that we don't care about which questions are marked correctly or incorrectly. So the answer is, I have 20 and I choose 7 of them to be correct. And this is exactly the same as if I have 20 and I choose 13 to be incorrect. And then exact same idea for part C. I have 20 questions and I choose 10 of them to be correct or incorrect, right? It's symmetrical. So we've got 7 nominees for 2 vacancies, 3 men, 4 women. In how many ways can the vacancies be filled? And then with various options. So because these 2 vacancies are the same, order doesn't matter. So we're just going to use choose. So for part A, we're going to have 7 people and we choose 2 of them. Now if we're restricted to only choose the women, then we have 4 options for the women and we choose 2 of them. And then for part C, we want 1 man and 1 woman. So for the women I have 4 and I can only choose 1 of them. And for the men I have 3 and I can also only choose 1 of them. And then we multiply these together. So we have 4 pairs of pants, 7 shirts, 3 sweaters. In how many ways may he choose 2 of the pairs of pants, 3 of the shirts, and 1 of the sweaters? So I've got 4 pairs of pants and I want to choose 2 of them. And then I have 7 shirts and I want to choose 3 of them. And then I have 3 sweaters and I want to choose 1 of them. And then we multiply each of these together. That's 17. 18. How many ways may 1A, 3 Bs, 2 Cs and 1 F be distributed among 7 students in a CTQR 150 class? So there's 7 factorial possible ways of rearranging all of these grades. And we have 1A, so we divide by 1 factorial, or we just don't do anything. 3 Bs, we divide by 3 factorial. 2 C's, we divide by 2 factorial. 1 F, we divide by 1 factorial. Right, to remove the overcounting. And this is essentially just because person 1 getting a B and person 2 getting a B is the same as person 2 getting a B and person 1 getting a B. Right, we don't need to count this situation twice. So 19, an art collector who owns 10 original paintings is preparing a will. In how many ways may the collector leave these paintings to the 3 heirs? So for each painting, we have 3 possible choices. So for the first one, I have 3 choices. For the second one, I have 3 choices, so on and so on, all the way up to the 10th painting. So the answer is 3 to the 10. A baseball fan has a pair of tickets to 6 different home games of the Chicago Cubs. If the fan has 5 friends who like baseball, how many ways may he take one of them along to each of the 6 games? So for each game, we have 5 possible choices. So we've got 5 choices for the 6 possible games. The answer is 5 to the 6. So how many subsets does a set with 8 elements have? So we can choose subsets of size 0, size 1, size 2, and so on, all the way up to size 8. And for each subset, I can choose 8 possible elements of the original set. So for the subset of size 0, I have 8 options and I can choose 0 of them. For the subset of size 1, I have 8 options and I can choose 1. The subset of size 2, I have 8 options and I can choose 2, and so on, all the way up to the end when I have 8 options and I choose all 8 of them. So now what we need to do is add all of these up. So 8 choose 0, plus 8 choose 1, plus blah blah blah, all the way up to 8 choose 8. And another way we can write this is the sum from k equals 0 to 8 of 8 choose k. So a fair coin is tossed 4 times. In how many outcomes do exactly 2 heads occur? So we want 2 heads and 2 tails. So we can think of placing 2 heads among 4 positions. So the first head has 4 possible positions to go. The second head has 3 possible positions to go. So the answer is 12. But the first head and the second head are indistinguishable. So we need to divide by 2. So the answer is 6. So we shuffle a standard 52 card deck. What's the probability that all 4 aces appear together in the shuffled deck? So the probability of this happening is the number of ways that the 4 are together, so 4 aces, divided by the total number of ways of rearranging these 52 cards. The total number of ways of arranging these 52 cards is easy, it's just 52 factorial. But how do we count the number of ways where the 4 aces are together? Well, what we do is we treat the 4 aces as a single unit, and then we shuffle that unit around. So then we will have 49 units that we want to shuffle around. So 48 of these are cards, and one of these is the 4 aces together. But then we need to account for the number of ways that the 4 aces can be rearranged themselves. So we need to multiply this by 4 factorial. So the probability will be 49 factorial times 4 factorial over 52 factorial. How many ways can 4 people sit in a row such that 2 specific people are always next to each other? Again, we do the same thing. We treat 2 of these people as a single unit, and then we find the number of ways of rearranging this new number of units. So we treat these 2 people as a single unit. We now have 3 units that we need to shuffle, so the answer is 3 factorial. But then for each one of these arrangements, these 2 people can swap seats, so we multiply by 2 factorial as well. Now we have a group of 6 boys and 4 girls to be seated in a row. How many arrangements are possible if all girls must sit together? So we have the 6 boys, there's the boys, and then we have the 6 girls, 4 girls. So we treat these, again, we treat them as a single unit. So we now have 7 factorial ways of rearranging these units. But then for each arrangement, the 4 girls can sit in different orders, so we multiply by 4 factorial to account for that. So we have a company with 8 engineers and 4 managers. How many ways can they form a 6-person team with at least 2 managers? So there's 3 cases that we need to consider. One is where we have 2 managers in the team, one is where we have 3 managers in the team, and finally when we have 4 managers in the team. So if I want 2 managers in the team, I take the 4 managers and I choose 2 of them, and then I take the 8 engineers and I choose 4 of them to make up the 6-person team. And for 3 managers, same idea, I take the 4 managers and I choose 3 of them. And then for each one of those combinations, I can take my 8 engineers and choose 3 of them, again to make up the 6-person team. And finally, we have 4 managers and we choose all 4 of them. And then we have 8 engineers and we choose 2 of them. So notice that these numbers stay the same. They're just the number of managers and engineers respectively that we're choosing from. And then these numbers, the number that we choose, add up to 6 in each case because we want 6 people in the team.